I wanted to bring out was this. Let's suppose that we restrict our attention to not only first-order equations, but first-degree equations. In other words, not only does the only derivative that appears be the first derivative, but it also happens to appear only to the first power. All right? Notice that in that situation, as I look at every term in my differential equation, they fall into two types. There'll be a term in which dy dx is a factor, or a term where dy dx is not a factor. What I can therefore do is collect all the terms which have dy dx as a factor and factor out dy dx. So I have a term of the form what? Some function n of x and y times dy dx plus what? A bunch of terms involving only x and y which have no dy dx in them equals 0. In other words, this is the most general form of my first-order, first-degree equation. If I now treat these as differentials and multiply through by dx, notice that I'm back to the standard differential equation form that we talked about. In fact, I'll bring this up again in a moment, in block 3 when we introduced exact differentials. Namely, I have an equation of what form? M dx plus n dy equals 0. By the way, to correlate this with our key theorem, notice that from here I could have written that dy dx was minus m of xy over n of xy. And that's the f of xy that I'm talking about in our key theorem that we talked about earlier. See, in other words, f of xy is the right-hand side of the equation when the left-hand side is specifically dy dx. So in other words, what I'm guaranteed of is this. As long as this function on the right-hand side is continuous, and its partial with respect to y is continuous, I'm guaranteed that this equation has a general solution. In particular, if m and n happen to be continuously differentiable functions, the general solution will exist, provided only that n and its partial with respect to y are not 0. Because after all, to differentiate this with respect to y, this is a quotient, and the only place that I'm going to be in trouble is that the square of the denominator appears when I use the quotient rule. So I have to be careful where either the partial of n with respect to y or n itself happen to be 0. But if that doesn't happen, it means there is a general solution. Now you may remember, back in block 3, we said, you know, if this differential happens to be exact, in other words, if there happens to be a function w such that dw is m dx plus n dy, then it's trivial to solve this equation. In particular, for what we mean by an exact differential equation is simply this. If m dx plus n dy is exact, then we call the equation m dx plus n dy equals 0, and